Yeah, welcome to a massive open online course on chemical process intensification. Here we will start the module 8 regarding interfacial area based process intensification. Under this module, the first lecture will be regarding the overview of interfacial area based processes and also how to create that interfacial area based on different mechanism, so that interfacial area will be the governing factor for any process intensification. So, as we know that approximately 2/3 of the unit operations performed in the process engineering that involves multiphase contact, like the distillation, adsorption, absorption, extraction, even some other chemical engineering processes, where interface is the main actually path to actually transfer the one component from the one phase to the another phase. So, in that case there are several mechanisms which may be actually imposed to generate this interfacial area in the multiphase systems. Now, that multiphase systems may be that gas liquid operations, liquid liquid operation, gas solid operations, and also gas liquid liquid operations, and gas liquid liquid solid operations also. So, all those multiphase operations mainly depends on interfacial area, because the chemical engineering processes mainly is governed by the mass transfer and heat transfer processes. So, that mass transfer and heat transfer depends on this specific interfacial area of the systems where that interface between the phases is created per unit volume. So, and also whenever these interfaces will be formed, of course, that the one phase will be actually traveling as a dispersed phase, and another phase will be as a continuous phase. So, the interface will be between that discrete phase and the continuous phase. So, like that if you apply some that absorption process of gases, that is, if you consider that physical operations like that absorption of carbon dioxide gas in the liquid. So, in that case to transfer that carbon dioxide gas to the liquid, that it will be through the surface between that carbon dioxide gas and the liquid. Now, that you cannot actually do that or you cannot produce that enough interfacial area if you simply supply that carbon dioxide gas just flowing through the surface of the stagnant liquid there. So, you may get some surface area, but that may not be the intensified way. So, to get that more interfacial area to absorb that carbon dioxide into the liquid through that interface, you have to think some other mechanism, so that you can increase that interfacial area. So, for that what you have to do, either you can supply the gas through the liquid as a dispersed phase of gas bubbles. So, if you produce gas bubbles through the liquid in which that carbon dioxide gas is absorbed. So, in that case carbon dioxide gas bubbles, whenever it will be produced in that liquid like amine solution or sodium hydroxide solution. So, in that case you will see that carbon dioxide gas will be dispersed as a dispersed phase of bubbles, and if you are producing more number of bubbles, you will see that you will get more surface area, more interfacial area between the phases of liquid and carbon dioxide gas bubble. Now, one bubble if you produce, there will be a surface area 4 pi r square, whereas if you produce from the same volume of carbon dioxide a large number of carbon dioxide gas bubbles, then you can get more interfacial area instead of that having with a single bubble. So, or you can think about that whatever you have produced without making a bubble, see what will be the intensification of that surface area production whenever it will be supplied horizontally over the liquid surface, and if it is supplied just by creation of surface area, just by forming of carbon dioxide gas bubbles and allowing to flow through the liquid. So, if you produce that more carbon dioxide gas bubbles through the liquid and if you allow it for flowing, you see what are the advantages. What advantages this, that here you can get more interfacial area compared to that just simply moving that gas through the horizontal liquid surface in a pool of liquid or over the pool of the liquid. Now, in a pool of the liquid, if you supply more bubbles, the advantage is that more surface area you can get, as well as if you control that bubble for flowing for longer time in the liquid, then you can get more mass transfer also. So, you can intensify the mass transfer process based on the increase of surface area as well as what is that residence time of the bubbles there. Now, if you supply that gas bubbles from suppose from the bottom of a pool of liquid by a certain mechanism, maybe gas distributor or other else. So, in that case you will see due to the buoyancy effect of the bubbles, it may go off immediately if its size is very large, but if its size is smaller, even finer, even micron in size, even nano in size, what will happen? You can get more surface area as well as more residence time of the bubbles, because smaller bubbles will give you the higher residence time, whereas larger bubbles will give you the less residence time in the liquid. So, just by creating that surface area in such way that more surface area whenever you are producing just by making a that bubbles or maybe liquids droplets, in that case you may get more surface area as well as residence time. So, both the effects simultaneously will give you the better performance of the mass transfer or any other chemical engineering process based on mass transfer. Even you may expect the intensification of the heat transfer also by getting more surface area through which that heat will be transferred. So, this is the mechanism, one simple mechanism by which you can get more interfacial area and residence time. But there are several other mechanisms by which you can generate more surface area between the phases and residence time also that you can control, so that you can get more mass transfer, more efficiency of the processes. So, that is why we have to think about that what will be the mechanism for that we can produce more surface area there. Now, if you consider that the imposition of acceleration field, in that case suppose if you produce that bubbles, there may be a certain force is applying there based on which that bubble is produced, interfacial area is produced. Maybe by that by forcing that liquid through the small geometry, and there will be a certain pressure drop between that the two sections, then you may expect that due to that pressure differences there will be a formation of bubbles. So, here what happened that we are just supplying some liquid from a certain location to the another location through a constriction, just by generating the acceleration field of that fluid. So, this is one mechanism, but in case of if you are not imposing that acceleration field, the system fluid dynamics may be dominated by the surface forces there. So, that the interfacial area development will be relatively small, and in that case with no buoyancy force there can be no counter current interfacial motion there. So, in this way you can think that some imposition of the acceleration field, like that shear stress, the frictional pressure, that maybe that ultrasound, maybe some ejector system inducing the gas and entraining into a liquid, that is also another mechanism. Maybe centrifugal force that may create that surface area. So, to actually intensify the performance of the operation, like reaction, separation, heat transfer, mass transfer, in that case you have to think about the the application of high acceleration field to simulate for the generation of the interfacial area by certain mechanisms. What are those mechanisms? That I told already that maybe ejector induced multiphase operating system. We will be actually discussing in details later on also. The next lecture will be coming with that ejector induced multiphase operating system, how actually that interfacial area is formed. In this case you will see that some liquid jet will be produced by supplying the liquid through the nozzle, and it will be actually passing through an ejector system, and whenever the liquid jet will come through the ejector system, that liquid jet may suck some gas from the atmosphere or from other sources, and then it will entrain or penetrate that gas into the pool of liquid, and during that penetration you will see there will be a surface breakup of that pool of liquid and entrainment of the gas as it is first phase of bubbles, and then that bubbles will be moving downward by downward movement of that liquid jet, and it will be flowing through the tube or column. So, that the formation of bubbles which will give you the interfacial area, as well as whenever it will be moving downward, at the same time the buoyancy force will try to move it up, and there will be a certain condition at which that this upward buoyancy force and downward liquid momentum may balance it, and it may reside for longer time in the column or in the system or in the unit. So, in that case you may get more residence time of that gases in the liquid, so that through the interface of that phases there will be a transfer of some components from the one phase to the another phase. So, this is the mechanism of that ejector induced multiphase operating system, by which you can create that interfacial area, and its application for different chemical engineering processes. Just simply that gas absorption may happen here, even sometimes liquid extraction you can do here. So, this is one mechanism. And also flow through rotating packed bed is also another important mechanism by which you can create more surface area. In that case, it may be vertical rotation, that is called toroidal, even sometimes it will be horizontally rotating packed bed. And other spinning disk reactor also, that is important. Some that absorption heat pump, that is called rotex. Motionless static mixer, that is also another mechanism by which you can produce more interfacial area. Micro channel based micro reactor, just producing that interfacial area and that making a plug flow, and then you can get the advantages of the reactions over there based on that interfacial area. Now, let us consider that motionless static mixture. In that case, the phases are mixed in the mixer, and this mixture will be so rapid, and in that case mixing can be achieved by action of splitting and twisting of the flow by that mixer element as shown in figure here. And you see that there will be some energy dissipation rate, and it should be very high, because you are applying this energy to split and twisting the flow by the mixer elements. And by splitting and twisting of the flow, you can have that formation of interfacial area there between the phases. In this case, you will see that energy will be very high. It may be, this is 10 to 1000 watt per kg, and also you can say that some other the convenient equipment can be used to produce that interfacial area, but that will not be comparable with this type of static mixture, because this static mixture may give you that maybe higher energy consumption, but it may give you that more interfacial area compared to the other equipment where less energy is consumed, like as a star tanks. Now, these large dissipation rates may give rise to the much higher mixing rates for intensified mixers when compared to the star tanks. Now, when two phases are mixed together like gas liquid, immiscible liquid, in that case a fine dispersion of the bubbles or drops in case of liquid phases and a high specific interfacial area can be produced because of that intense turbulence that is created by that mixing elements inside the static mixer. So, there may be high turbulence, and also there may be shear of that liquid element with that mixing elements, and based on which that you can get that more surface area just by forming bubble and droplets. That is why in this case you will see resistance to the interface mass transfer is considerably smaller than in convenient equipment here. So, you are getting, you will see that more finer interfaces, that is very thin layer between the liquid, and that mass transfer will be through the thin film of region of that interfaces. So, that is why this the resistance of the interface for the mass transfer will be less compared to the other equipment where that mass transfer is taken place through the interface. So, we are getting here very interesting point here, that bubble drops may give you that resistance to the interface mass transfer relatively smaller compared to the other equipment. So, this is one of the important mechanism by which you can create the interfacial area between the phases. In addition, a wide range of gas liquid flow ratios can be handled here, whereas in star tanks the gas liquid flow rate is often limited by the onset of flooding. So, if you are applying that star tank reactors instead of that static mixer, so you may get that flooding condition in the star tanks. And also in case of static mixer oriented interfacial area production may give you the higher mass transfer coefficient. It may be within the range of 10 to 100 times higher than a star tank reactor. So, we are getting that one mechanism here, just the by static mixer how to produce that surface area for the process intensification. Now, we have already told something about that ejector induced multiphase operating system there. In this case, the figure shown, we are thankful to the investigator of that or report by Stankiewicz and Moulin in 2003. They have given this that ejector induced multiphase operating system, where it consists of 4 main sections. One is the spinner, that is orients and stabilizes the flow. Here as shown in figure it is shown, and nozzle, there I think it is there nozzle, and this nozzle, it provides a high velocity jet of the fluid. Gas chamber, the high velocity jet that may creates suction in the gas chamber that entrains gas into the ejector. So, this type of ejector system, here you will see due to the pressure difference and sucking the gas into the pool of the liquid and then passing from the higher pressure to the lower pressure, and you will see that there will be a that pressure, due to this pressure differences there may be a formation of that bubbles if it is gas liquid operation, droplets if it is a that liquid operations, then you can get this type of that system for the interface production. And then after production of that that interfacial area, that is by making that bubbles, it may leave that gas chamber and the liquid jet that attaches itself to the mixing tube wall, resulting in a rapid dissipation of kinetic energy and creating an intensive mixing zone that known as mixing shock region there. So, whenever it will be released from that that ejector system after sucking, you will see that there will be a zone in the tube here in this location, here in this tube, in these locations you will see there will be a gas liquid mixing, intense mixing will be there, and from this jet from here, whenever it will be plunging in the pool of the liquid here, at this that pressure differences and just breaking of the pool of the liquid and entraining the gas into the liquid and making that formation of the bubbles and formation of the interface, you will see that bubbles will be there in the mixing zone in the tube, and this mixing zone will give you that intense mixing of the phases of that gas bubbles and the liquid due to the high kinetic energy dissipation that is supplied by the liquid jet as per kinetic energy of the liquid jet. So, this that mixing zone, it is called intense mixing zone, may be referred as the mixing shock region. So, in this case high turbulence is created, and based on that high turbulence and the that high kinetic energy distribution, in this region, the breakup of that formated bubbles will be there and producing that fine dispersion of the bubbles, and consequently a large interfacial area will be generated, which will be more beneficial for the mass transfer. Now, if you compare that ejectors and motionless mixers, you will see it may be have similar mass transfer performance at a given gas liquid flow ratio and energy input. And the reaction engineering process that proceeds in three major types of the equipment like mixer settler systems, column extractors and centrifugal extractors, and where you can produce that interfacial area based on this static mixer, even that ejector system, and also that some other centrifugal field, where you can apply those things for the intense mixing, for the better mass transfer, for the extraction process, and also that combination of the that reaction and extraction, both also there may be at a simultaneous condition. Now, counter current column extractors can be further subdivided into non-agitated, non-proprietary columns and agitated proprietary extractors. So, this is also another important point to be actually noted here. Sometimes you will see that some systems will be agitated, some systems will be non-agitated. Like static mixer, that is that is non-agitated system, whereas the liquid or ejector induced or jet induced gas liquid operation are called agitated systems. And they are that in agitating system that the liquid systems will be broken up into a finer droplets or finer bubbles that may increase the interfacial area to improve the mass transfer, and also if its reactor efficiency. Various forms of energy inputs may be imposed for the formation of that interfacial area, like rotation of the propellers, impellers, and these pulsation mechanism, vibration also it may be there, even ultrasonic device, even centrifugal device also may be used for that creation of interfacial area for the better mass transport. Here you will see some figures as per that Stanquist and Moslin in 2003 when they are actually discussing about that re-engineering of the chemical processes in the plant, and they have published those things in a book like as a re-engineering the chemical processing plant. In their book they have actually reported that this agitated extractors and the non-agitated extractors there. So, here agitated extractors may be that like rotating disc column here, even maybe some other column like vibrating column, and also that Cooney rotating extractor column, Siebel extraction column, also Rustan that extraction column, core extraction column, those are agitated extractors where you can produce more interfacial area based on that rotation. And for non-agitated extractors like that static mixer, even spray column, where from the nozzle that droplets will be sprayed and it will be that allowed to flow in a certain direction or vertically upward or that downward, and during that flow and residence time of that droplet there may be a mass transfer between the phases of that droplet and other liquid. And also packed bed, here in that case that the liquid will be spread through the bed of packing material to get the uniform distribution of the liquid throughout the bed, and so that it may get the contact with the solid surfaces well in good condition. But there may be some advantage disadvantage of those packing column packed bed systems, and in that case that may be sometimes it is being intensified to avoid all those disadvantage there. Sometimes now it is that rotating packed bed is coming, even it may be horizontal or vertical toroidal packed bed, that may give you the better performance compared to the conventional packed bed system. Even sheep tray, you will see there that distribution of the vapor or gas through the that plate or tray through which there will be porous plate of those you can get that formation of bubbles or droplets through that tray, and that droplet will actually produce that more interfacial area and get the intensification of the mass transfer and chemical engineering processes. Now, the changes in the reactor design may also give you the sometimes better performance of that chemical engineering processes based on the mass transfer. And if you change that reactor design from a mechanically agitated vessel to a suppose bubble column reactor, where gas is distributed from the bottom of the column through the distributor as a dispersed phase of bubbles in a continuous liquid or in a stagnant or in a pool of liquid, you can say that it can be observed that as a result of the higher interfacial area that is available in the bubble column, that you can apply this that high interfacial area for the increase of that is efficiency of the mass transfer and consequently the chemical engineering process performance. So, that is why the design of that equipment you can think in novel way how to design that equipment to get the better way of mass transfer just by creating the that more interfacial area, and also case to case where that residence time will be required as a low or high. So, accordingly you can devise, you can design different types of that column or reactor to produce that interfacial area. Now, I told that there will be certain that disadvantage of that conventional packed bed. Now, to overcome all these, that sometimes the concept of rotating packed beds are coming, and it raised considerable interest for counter current gas liquid contact. In that case, torus like packed container was first proposed in UK with rotation about a vertical axis, it is called toroidal packed bed, and in that case in a patent that it is given that liquid into the inside cylinder surface of the bed is forced to flow radially outward under the influence of the centrifugal field, and whatever gas is introduced at the outer bed surface, that may be flow radially inward due to the imposed pressure gradient, and also rotation of this column may give the advantages of the formation of this interfacial area and also distribution of the liquid through the column, and so that maximizing the utilization of the liquid to get contact with the gas and also solid surfaces. So, in that case rotation may be of about 50 to 2000 rpm, that may give the centrifugal acceleration of the 60 to 1000 g. G means here gravitational acceleration here, Now, it is possible that an increase of that both the effective gas liquid interfacial area and of the liquid side mass transfer coefficient that may contribute to such large mass transfer rates. So, this is the advantage for that rotating packed bed, whereas horizontal rotated packed beds also nowadays is coming. In this case, Hirata and Hosaka in 1991, they have applied this that rotation of the packed bed horizontally to get that more efficiency of the chemical engineering process. In that case, they have applied some biological treatment of wastewater, and in that case they have actually used that, or they have designed that rotating packed bed which will be partially or immersed in liquid, while the rest is exposed to the atmosphere. Now, in this case you may get that more uniform liquid distribution in the packing under well controlled conditions. So, this is the advantage over that vertical rotated packed bed. Other important mechanism to create that surfaces to get more contact with that phases of the solid surfaces or catalyst surfaces with the liquid or gas. In that case, a spinning disc heat transfer surface also important, through which there will be the transfer of heat through the surface. In this case, overall heat transfer coefficient is about 10 kilowatt per meter square K for low viscosity process, fluids and water for or you can use glycol as a heat or cool fluid, or other fluid also you can use this type of that spinning disc reactor. This is spiral reactor, and here see through that channel there will be a that flowing of cooling liquid to that transferring of heat from that higher heated element to the lower heated element. So, in this case the heat transfer from the higher temperature to the lower temperature can be done by this that spinning disc reactor. In this case, very interesting that there may be secondary flow will be produced, and which will give you that more that transfer processes there. And generally that 0.5 meter diameter disc with delta T that is of 20 K, that means temperature difference of 20 K may transfer 39 kilowatt. As per actually this Doble in 2007 report, they have actually given this idea for the spinning disc reactor for the process and operations in intensified way. That other way, that spinning disc reactors are operated generally horizontally or vertically and are mounted on a rotating axle, and in that case liquid is fed near the center and flows across the surface of a spinning disc under the influence of centrifugal force. And this force may be stresses and spreads the film, and this film whatever it is produced, this liquid thin film you can say, it may allow that for high rates of mass transfer, so that it favors unit operations such as absorption, stripping, mixing and reactions, just by getting more contact of the liquid with the that surface area just by uniform distribution of the liquid, and also getting that more uniform mixing of the phases, and also that interfacial transfer. So, in this case residence time on the disc may be in the ranges of 0.1 to 3 second as per their observation. Now, electrical field based surface area also very important there, that mechanism also are nowadays very interesting, or focusing by the that various research organization to use that electrical field for the separation processes, just by producing that more interfacial area, just by interacting of the fluid element and also you can say that contacting of the phases just by this electrical field. So, in this case intensification of the electrical field separations has focused on improved design for the coalescing vessel and the electrodes that enhanced hydrodynamics to promote electrically charged droplet interactions through turbulence and higher electric field strengths. And the large interfacial areas that forms due to small droplet formation in electrical fields that can also be beneficially applied to enhance the overall rates of reaction in immiscible that liquid systems, whereby a higher degree of stable emulsification is achieved there. So, in this case some process that involves the enzymatic hydrolysis. I think you know that enzymatic hydrolysis of triglyceride esters that may give you that free fatty acids and also glycerol. So, in that case electrostatic fields are used to intensify the dispersion of the aqueous phase into the oil substrate by creating large interfacial areas between the reacting species. Another important mechanism to create that surface area, it is called that microchannel based surface area. Already we have discussed in our previous module that microchannel based monolithic reactor, where how that that interfacial area is being produced by making that slug flow of liquid and gases, and how that mass transfer is being happened through that interfaces of the gas and liquid in the monolithic catalyst bed reactors. So, that microchannel based micro reactor, that is are actually procured where that reactions may be possible based on that interfacial area. So, in that case a mixture of the reactants that enters the reaction zone, which provides the sufficient residence time for the reaction to produce, and in this case the simple channel typically suffix for the homogeneous reactions, whereas flow obstacles in the channel may be packaging, you can refer it, is useful to increase the interfacial area in heterogeneous reactions. And in this case transport of the fluid elements within the micro flow due to the deformation with elongation of the fluid elements, which increases their length and decreases their width, that may yield you higher interfacial area. And in this case due to the small dimensions of the micro channels, this that Reynolds number values, that is depends on velocity of the fluid, even geometry of the fluid and properties of the fluid, are particularly low, which may imply the laminar flow, and in that case molar diffusive flux that will dominates the mass transport within the micro channels. That is why this molar diffusive flux is based on that Fick's law and is a function of the diffusion coefficient of a certain molecule and interfacial area. So, this interfacial area will actually give you the that enhancement of the mass transfer based on this diffusive mass flux. Now, if you think about that oxidation of olefins by ozone, that may be the one of the example of a useful reaction that can be difficult to run in a conventional reactors, because of the high heat of reaction that is generated during that ozonation process and the potential of high reactive site production that form based on this exothermic reactions, like peroxypolymers there for an example, that is produced during this oxidation process. However, in this case it has the advantages of high selectivity and generation of oxygen as the only side product there. So, the high surface to the volume ratio in the micro reactors, you can have the increment of the gas liquid interfacial area that may enhance your mass transfer flux or mass flux, you can say, of the ozone through the interface, and it facilitates the removal of the heat generated by the chemical reactions. So, the oxidation of the olefins by the ozonation, which is exothermic reactions, that may be that heat productions will be higher, and then reactive site production formations will be there along with that high temperature. And now, to reduce that temperature, you are just using that high surface area to the volume ratio in the micro reactors to increase the gas liquid interfacia, that may enhancing the mass flux of the ozone through the interface, as well as it may be useful for the removal of heat by the chemical reactions through that interface. So, this is the advantage of that production of the interfacial layer through the micro channel. Now, another important mechanism, it is called ultrasound based surface area. This ultrasound that has the ability to form the fine emulsions like liquid or gas liquid, or that gas liquid solids, there is this slurry systems there. You can use that ultrasound to make that emulsions, that may be liquid phases. So, thereby increasing the interfacial area of the liquid interface, like droplet. One liquid may be more lighter liquid will be that discrete phases, just forming that lighter liquid droplet, and their interfacial will be there. So, that interfacial area may be available for the reactions which can switch reactions involving that phase transfer catalysis. So, I think we have discussed a lot of things about that mechanism of formation of interfacial area, and how that interfacial is related to the mass transfer processes. So, we will discuss more about that application of that interfacial area, and also the specific that design of that reactors, or you can that unit by which you can that produce that interfacial area, as well as you can increase the residence time, and so that you can apply this mechanism of formation of interfacial area for the chemical engineering process intensification. So, next lecture we will discuss more about that interfacial area based chemical engineering process and unit design. So, I would suggest to read further about this interfacial area based chemical engineering processes from these references. Even you can follow other reference also to get more information about the interfacial area based process intensification. So, thank you for your attention here.